Morning, everyone. How are we doing so far? Questions before we start? Doubts, suggestions, queries? Within variation, between variation, everyone comfortable with the concepts? Right? Okay. So I want to exploit within variation. What do we do? So an ancillary thing which is associated with this is this potential problem with exogeneity, right? So there may be omitted variables out there. If these omitted variables are somehow have no within variation, then what we can do is we can remove all the within variation from the data, right? So that is what we have been doing. How do we do that? Well, we have done two different transformations to achieve that. One is first differencing, and the other one is fixed effects transformation. Okay? So if you have a full, strict exogeneity condition, then which one is more efficient? Fixed effects is more efficient, right? Okay, because it is making full use of the moment conditions, right? First differencing is only using some of the moment conditions. That is sufficient to remove within variation, right? But then it is not using the full set of moment conditions, and therefore fixed effects is more efficient. On the other hand, the strict exogeneity condition underlying fixed effects can be a bit strong, right? Okay, and there may be situations when it may be better or preferable to use the first differencing transformation. Remember the moment conditions at the back of your mind, because we are going to return to these moment conditions repeatedly today, right? The first differencing moment conditions, the fixed effects moment conditions. Everybody together on that? I don't have to go over that again, right? So that we have covered last time. So we are going to take that as a given, and that will be the starting point for today's lecture. Okay? Everybody on the same page? Okay? Right. So when we did fixed effects, what did we do? What was the transformation? We were doing demeaning, right? So what is demeaning? We were taking the mean out, all right, from x and from y. So from xit, what did we take out? X bar I. Okay? And from YIT, what did we take out? We took out Y bar I, right? And we saw that by taking these means out, okay, so what did we do? We removed all the between variation from the data, right? Okay? So if taking the mean out removes all the between variation from the data, where is the between variation sitting? Obviously it is sitting in the means, right? If you want to extract all the between variation rather than take it out, what would you like to have, look at? You would like to look at the means themselves, right? That is where all the between variation is. Okay, so we start off from the point that maybe, so we have effectively exploited within variation, but the two ways by which we exploited within variation, we realized that both of them actually took all the between variation out. Now, in some data sets, for some variables, there might be useful information in the between variation as well. Maybe the same kind of information, maybe different kind of information. We talked about whether the between effects estimator or between effects beta should be the same as within effects beta. We don't know about that. But then there is certainly, in some context, there's going to be some useful information about beta sitting in the between variation. So the question is, how do we extract that information? All right? Throwing it out is not necessarily always useful. Okay? So we are going to now start looking at estimators which exploit the between variation. Okay? So the first interesting idea that we have is that all the between variation is surely sitting in the means. So let us find out what is there in the means. Okay? So what do we do? So the between estimator, what it does is, it runs a regression of Y bar on X bar. You see, all the between variation is in the means, right? So if you run a regression of Y bar on X bar, that must be giving me an estimator which comes only from the between effects. Okay? So now, under the context of our inner components model, if we write this down in this way, right, we have a model where YIT is a function of XIT and an error term which is a composite error term, right? So there's individual specific heterogeneity and there is a completely idiosyncratic term. So this is my epsilon, right? So what is epsilon bar? Well, epsilon bar, this error term here in the mean equation, that must be this, right? Okay, guys? Right? What kind of an equation is this? How many observations do we have here? N observations, right? One for each individual, right? You see, we threw out N observations earlier. You remember that? We reduced our degrees of freedom for fixed effects or for first differences reduced by N. Why? We threw away one observation notionally for each individual, right? What is that observation? That is precisely this observation. So we are pulling this up now. There are N observations, one for each individual, right? Is there any hope of estimating this guy? separately alpha I, no, there is no hope, right? There's an error term here, idiosyncratic error term, and there's this guy, so means everything, the error term is together, right? I have no hope of separately identifying those two. So we return this in the error term here. And now we want to conduct OLS here, right? So the OLS for the group means. So there will be some moment conditions, orthogonality conditions under which we can do this. And what is the principal orthogonality condition? This guy, so this guy is completely idiosyncratic, right? This is not related to anything, right? But the important assumption has to be that this guy is uncorrelated with this guy here, right? So it's orthogonal with xi bar. Right? If alpha I has to be orthogonal with xi bar, it has to be orthogonal with xi1, xi2, so on up to xit, all the time points, right? Those are the components of xi bar. All right? So the between estimator then uses the moment conditions, expected value of xi bar, epsilon I bar, that is this guy, that is 0. Okay? Which essentially amounts to two moment conditions. One, that this guy is orthogonal to alpha I, and the other one is that this guy is orthogonal to the average of the idiosyncratic errors. This one is relatively innocuous, right? Because under the assumptions of our model, error components model, this guy was purely idiosyncratic, right? Okay? But this one is potentially problematic. Okay? So, these are the two moment conditions. Which one bites? Well, this one doesn't bite too much. Why? Because as t goes to infinity, this one here is going to become closer and closer to 0, right? Okay, because this becomes closer and closer to 0, there is very little information in this moment condition. So really the important moment condition is this. All right? Now what is that moment condition? That is the between identifying variation. Right? So this essentially depends on between identifying variation. Okay, so between estimator, very simple, right? Very simple to use. One has to be careful about the underlying moment conditions. Okay, so what is the conceptual setting? Well, essentially when we did exploited within variation, we saw that the way to, the most efficient way to utilize within variation was take the means out, right? So if the means, taking the means out removes all the between variation, then all the between variation must be sitting in the means. Okay? So that is what we try to exploit here, right? So run a regression on the means. So that is a between estimator. Okay? So think about some data set that you have at hand. Okay? You have done fixed effects, let us say. We are using the full, exogeneity conditions. Fixed effects, if you are not happy with that, do first differencing, it does not really matter. But essentially you have used the within variation. Then you realize that there is a bit of between variation there which might be useful. For example, you might be regressing wages on various factors, including education, and there is very little. There is a little bit of perhaps between variation well, the large part of the variation is between, right? So you have essentially removed education, which is not ideal. So you want to explore that. How do you explore that? A simple way of doing that is this. However, the moment you do this, you have to make this assumption. And this assumption is crucial. Okay? So if you did fixed effects and found that, well, have you started doing fixed effects in Stata? This week, right? So you will see that after your fixed effects estimation, Stata immediately gives you a test of a hypothesis that these guys are important. Right? There is individual variation, right? So suppose that hypothesis, the null hypothesis that they are not important is not rejected, then you can go ahead and do your between estimator as well, estimate your between estimator, right? Otherwise you have to be a bit careful. Okay? Union membership and wedge determination. We have seen this example several times. All right. So now what do? We apply the within transformation. We apply the between transformation to the data. What is the between transformation? That is simply taking averages. See, all the t drops out. Yeah, because it's one observation for every individual. Okay, we are now going to apply OLS to this. There are n observations. All right. See that you don't need group mean for education because there is no, it doesn't change over time. All right. So that is how you do your between estimator, right? So you are using between identifying variation, right? So we are able to obtain estimates of the intercept beta 0, right? And return to the time invariant education beta 1. You would of course be worried about endogeneity here, right? Okay, for the same reasons as we have discussed, right? What about the interpretation? The interpretation is the original interpretation, right? So just the important thing to care about here or to think about here is that you are estimating a between effect, right? But in the context of the original model, the interpretation of betas is exactly the same. We are making transformations every time, but the betas are not getting transformed. So, so the interpretation is just like its interpretation in our underlying structural model. Okay. What else do we have? Experience is the average years of experience. Yeah. So there is no trend growth rate here. This is all individual level data. Okay. The important thing to think about here is where is the information or where is the estimate coming from, which kind of variation, right? And you have to think through that. And that is context specific. Every different regression model, every different context will be different, right? So you have to think through what is going on there. Okay. This is an illustration of the interpretation in the case of union. Right, union membership, and remember that union membership in principle had both within and between variation, right? So earlier we have talked about within variation for union membership, and what was that? That was people who moved from a unionized job to a non-unionized job, or people who moved from a non-unionized job to a unionized job, or people who joined the union. Okay? So that was within variation. Now we are exploring between variation, and between variation is the variation across individuals, okay? Okay, between estimator. Everybody comfortable with that? Okay, now the next question is, can we do something slightly better than the between estimator in exploiting between variation? This is a bit of a subtle point, okay? So just bear with me for a few seconds and pay attention. What was our underlying model? Our underlying model was this, right? When we extracted the between variation from the data, what did we do? We took the means and put them into a regression model, right? Once we put them into a regression model, we sort of forgot that our underlying data was actually a panel, right? Okay? By forgetting this information, we are losing some information, right? So by forgetting this context, we are losing some information. And we are going to try and pull that in now to try and get a perhaps more efficient estimator. Okay? So let us see how we can do this. So we are back to our original model, right? We are treating our error term as a composite of two objects. All right? What are those? This idiosyncratic error term and this individual specific error term. Now, what was the crucial moment condition for the between estimator for exploiting between variation? It was that your xit was orthogonal to your alpha I, right? So the idea now is, let us go back to this and impose this directly here. Okay? So first of all, we assume that our eta it, the error term, is conditionally homoscedastic. This thing here. Similarly, as with fixed fx, the error term is spherical. All right? Assume that as well. Okay? We assume that these alpha guys, they have a variance. Okay? They have a finite variance. So that is this one. And set the mean to 0. All right? Which is the same thing as doing what? Including an intercept in your x, right? Okay, so there's a beta 0 out there in here. Okay? This one is mean 0. This is the variance. Right? And now under the assumption that these alpha i's are orthogonal to the x's, we can do a feasible GLS here. Now what do we mean by feasible GLS? Essentially what you have to do is to split the overall variation, the variance of this error term here, into two components, one which comes from alpha and one which comes from eta. Is that possible? Well, that is possible. Why is that possible? That is possible for the same reason as fixed fx was possible. See, the point is that if n was finite, then this guy is identified, right? So you can obtain an estimate of this. If we can obtain an estimate of it, of course we can obtain an estimate of its variance across the entire set of panel units. And that is precisely this. If you can obtain an estimate of this, you should be able to split this up because you can obtain an estimate of this as well, right? So, but what moment conditions shall we use here for feasible GLS? So, moment conditions for fixed effects estimation was this guy, right? For the random effects estimation, we use this plus this one. So, the within moment conditions and the between moment conditions. So, the random effects estimator basically uses within moment conditions and between moment conditions, both of these. What about efficiency? This is going to be more efficient than fixed effects, right? Why? Because you are using more moment conditions, right? Provided, of course, that these moment conditions, additional moment conditions are valid, right? Okay? So these moment conditions utilize the within variation, these moment conditions use the between variation, so you're using both. How many moment conditions are there? KT square moment conditions. Okay, how many parameters are there? There are K parameters that you are estimating, right? Okay, so how many over identifying restrictions are there? T square times K minus 1, right? Okay, which is positive. Okay, if you have a constant term anywhere there, right? So if you have one regressor, then it becomes positive. Okay? So what can you do now? You can test these moment conditions as well, right? Because you have a lot here. Okay? You know this Sargan-Hansen test, right? So for over-identifying restrictions, right? We're going to use this in a little bit. So that is fine. So we're going to see in a few minutes how we do feasible GLS here. But this seems quite plausible, right? This is something that we can do to efficiently utilize all the moment conditions which are there. In the process, we are going to obtain something which is more efficient than random effect, more efficient than fixed effects, more efficient than between effects as well, right? Okay, but the question is, why should we be reluctant to use this moment condition? Well, because in many economic situations we really don't believe this. See, the point is the following. If this condition were correct, then we could have done pooled OLS as well, right? The reason we moved out of pooled OLS was because we suspected that there might be individual specific heterogeneity which is potentially correlated with the included regressors. For example, if you are regressing wages on education, you might think that there's ability sitting in there which must also affect wages, and ability is of course going to affect, is going to be correlated with education. So there's going to be a problem here, right? So that was our first point of departure. So because of the same reason, we might be quite hesitant to impose these additional orthogonality conditions. Is there a way we can test this? Well, there is of course a way that we can test it. Okay, what kind of test is that going to be? How do you test a set of orthogonality conditions out of a series of them? Only some of them? What is the C test? Okay, the Hansen-Surgan is really for a complete set of orthogonality conditions. You cannot say which ones are correct and which ones are not from that, right? There's a more specific test which is suitable for specific orthogonality conditions, and that is Hausman. Okay? Can you do Hausman here? Well, you can do Hausman here, right? Because if both moment conditions were correct, then the random access estimator, which uses the full set of moment conditions, is going to be efficient, right? All right? On the other hand, if this condition was not correct, then random effects is going to be inconsistent, fixed effects is going to be consistent, but it is going to be inefficient under the null hypothesis, right? So therefore you can use a Hausman test here, right? So we're going to come back to that. So sort of argued that, well, what is the use of this between group moment conditions, because they are kind of a bit dopey, right? So we do not always believe them. Well, you might want to use them because of two reasons. One is that it leads to a more efficient estimator, and of course we can test whether the additional moment conditions are correct using a Hausman test. That is one situation. The other one is sometimes you have just between effects, right? So if you have just between effects, for example, race or gender in a wage equation or even education, then there must be a way of utilizing that information. Okay? There's something that I'm not covering here. Both the between effects estimator and the random effects estimator are not quite ideal, right? Okay, so we are going to see several examples of this, but I'm not going to go further than this here. But I'll just mention in passing that there is another estimator called Hausman-Taylor, which is probably the most popular and best known way of extracting between variation in complicated situations, right? So I'm not going to talk about it. Okay. So now let us see how we implement this random effects estimator. Okay, and in the process we are going to look upon random effects as an efficient GLS estimator. So remember that we have assumed this conditionally homoscedastic and spherical errors, right? We have also assumed this, okay, that there is some variation in this alphas, right? What happens if there is no variation in the alphas? If this guy is 0? There is no alpha here, no? It is all pulled into your beta, so then you are in the pooled OLS situation, right? Okay, so that is not very interesting. So now, this error term here, its covariance matrix is this, conditional covariance matrix. And what is that? That is sigma alpha square JT plus sigma eta square IT. What is JT? JT is a T by T matrix with all ones. Okay? Okay, so this turns out to be this guy here. Okay? So you can see this easily. So by writing this down, so this guy is this times this one here. This one is a column vector, this one is a row vector, All right. So what do you get? The whole thing that you get is this matrix here. All right. So the diagonal elements are sigma alpha square plus sigma eta square, and the off diagonal elements are all sigma alpha square, right? So that is why this is sigma alpha square jt plus sigma eta square it. Now the moment you look at this straight away, it is obvious that suppose we could get a handle on these residuals from this regression model, we should be able to estimate separately these two guys, right? In a feasible way, in a consistent way. The moment we can estimate those separately, we can plug them back in and do feasible GLS. Okay, so that is the point. All right. So sigma nt, the nt by nt variance covariance matrix of the full error term will have this block diagonal structure then. All right, which is sigma alpha square, the identity matrix Kronecker product with jt, plus sigma eta square, the identity matrix Kronecker product with it. Okay. So in order to do GLS, what do we need? We need sigma inverse, right? The inverse of this guy, the inverse of the error term, right? So because we want to pre-filter, right? Okay. And we need a matrix square root of that, right? So inverse and the square root of the inverse. Okay. This is a huge matrix, right? So this is a nt by nt matrix. So we are not going to ask Stata to do it for us because it's huge, all right? But this comes out in a very simple form. Okay, so the derivation is shown in Baltaji's book. So this comes out to be like this, right? Where this sigma 1 square is precisely this guy, t times sigma alpha square plus sigma eta square. All right. This p and q are the within projection and demeaning matrices. Okay, so that comes out in a simple form. So don't need much things here. All you need is an estimate of this guy. Okay, and an estimate of this. That's all you need. Right? So how do we now do GLS? Well, what we are going to do is we are going to pre-multiply the estimating equation by this guy, right? And then estimate using ordinary least squares. Okay? What is the crucial element here? This one. What is that? Sigma 1 square is this guy. What is sigma 1 square? Sigma 1 square is the total variation from the error term, right? Okay? And sigma eta square is the variation from the idiosyncratic part. Okay? So this thing here is a measure of how important the idiosyncratic part is to the total variation. Okay? So, pre-multiplying this now is the same thing as doing quasi-demeaning. All right? With a particular theta, and that theta is this guy. Okay? So this theta is 1 minus sigma eta divided by square root of this. Okay? And this is between 0 and 1. So remember, when we did demeaning, we said, well, there might be contexts in which we might not want to take out the whole of the mean. So now you see a context where you don't want to take out the whole of the mean. You want to take out only theta part of the mean, right? And that is the context of random effects estimation. Okay? So in order to get this random effects estimator, what we need to do is, first we need to obtain estimates of this guy and this guy. Okay? How do we obtain those? By inefficient first step estimators. Okay? And then you combine them to get a theta hat. Once you have got theta hat, you plug this in here and do feasible GLS. Together, everyone? Okay? How do you get this first stage inefficient estimators? How do we get a first stage inefficient estimator of this? Inefficient in the sense that you are not using the full set of moment conditions, right? But at least it has to be consistent. How do you get that? So what are the assumptions? What are the moment conditions you have used? You have used these two moment conditions, right? Under these two moment conditions, what happens? This error term is orthogonal to the x, right? Because both components are orthogonal to x. Okay? So what can you do here to get a first stage inefficient but consistent estimator? You don't even need to do fixed effects, just ordinary least squares. Guys, are you following this? Yeah? So just ordinary least squares is going to be fine, right? So you just do OLS here. Yeah, that is going to be consistent under the assumptions of the model. And what are the assumptions of the model? So both these two moment conditions hold. All right? Once we have obtained these estimates of the beta by ordinary least squares, we can extract the residuals. All right? Once we have extracted the residuals, then of course we can split this out, right? We can take each individual unit. See, the residuals are 0 on average, right? But that is average across all the NT observations, right? But they are not going to be 0 on average for each individual, right? You take one individual, okay, average the residuals, that is going to give me an estimate of this guy, right? And the variation of that across all the individuals is going to give me sigma alpha square. Once I have that, then I know how much variation is in the other part, idiosyncratic part, and I can estimate that as well. Okay? So that will simply give me estimates of these guys, right? And then I can go ahead and do quasi-demeaning based on an estimated theta. All right? Is this how you do it in practice? No, you don't. You do slightly better, right? But that's fine. Okay? Okay. So that is random effects. Right? So now we have two different ways of extracting or exploiting the between variation in the data. Okay, so we saw two different ways of exploiting the within variation in the data. One was first differencing, one was fixed effects. Then what did we do? We looked at only the between variation and exploited that, and that gave us a between estimator. And random effects is actually something which uses both the between and the within variation, right? But it is still making full use of the between variation, and under the context when it is valid, it is a very efficient estimator. Okay, so it is the most efficient estimator. Okay, so the random effects estimator is obtained by OLS on the quasi-demeaned data, right? So what is quasi-demeaned? So these double dots here, YIT minus theta times YI bar, right? And XIT minus theta times XI bar, where this theta is this guy, okay? And this has to be estimated, right? So we can do a first stage, consistent estimation of this, and then we do feasible GLS. Okay, let us now look at a few special cases.
Could you maybe explain once again how we can get from the, so we do OLS in the first step?
Yeah.
And then but how do we come from OLS to the sigma eta or sigma alpha again?
Okay. Yeah, no, sure. Why is this not working? I think I'll just stop here. Okay, so you've done the OLS, right? You have got your beta hat. You have got your beta hat, then you have residuals. All right? These residuals are going to be 0 on average across the whole data. Right? We know that the residuals, though, are a combination of these two guys. So how do you get your alpha I for an individual I? I'm now interested only in my individual 1. How do I get an estimate for this alpha 1? This thing is 0 on average, right? So if I average all the residuals for observation 1, individual 1, that gives me an estimate for this guy, right? So I do this for all the individuals, and then I compute their variance. And that gives me my sigma alpha square, right? Okay? Why can I do this? I can do this because I can get a first stage inefficient but consistent estimator by doing ordinary least squares. Is that clear? Sure? Okay? Yeah, please.
So I had the epsilon, the residuals, and then I split what I estimated into to just look at the individuals.
Yes.
Alpha.
Yeah. Okay. So individuals. So if you're looking at one individual panel unit, all right, so that has epsilon I 1 hat. So we do not really get the epsilons, right? We get the residuals, right? Whatever you call, in your notation, what do you call it? E or whatever, yeah? So EI1 through EIT. Now the average of this EI1 through EIT is going to give me an estimate of this alpha I, right? Because the idiosyncratic error is going to cancel out, right? Okay, so that is how I get an estimate of that. And then I look at the variation of that across all the panel units. That is going to give me sigma alpha square. So I get my sigma alpha square. If I get my sigma alpha square, at the same time I can get this as well, so the sigma eta square, right? So I can split the two up. Okay? By the way, that is not a very nice way of doing this. But there are slightly better ways of doing it, and that is how Stata is going to do. I'm not going into that right now. But I'm at least showing you one way to do it, okay? I'm just going to go through this slide and then we'll go into a break, right? Okay, so, but let us think about, do a few thought experiments here. Suppose my sigma alpha square was 0. So back to my model again. What is my model? My model is yit is equal to xit prime beta plus alpha I plus eta it, right? It's a composite error term. Suppose this guy is 0. What does that mean? That means that there is no variation in this alpha I, which means that there is no alpha I, right? There is no individual variation at all. Okay? So if you substitute sigma alpha square equal to 0 here, what happens? Your theta becomes 0. So what are you doing here? You are regressing yit on xit. What estimator is that? That is pooled OLS, and that is precisely what you should do because there is no individual variation, right? Unobserved variation. Okay? So the efficient GLS estimator in that case is exactly ordinary least squares. Let us take the other extreme, where this theta is very close to 1. When is theta very close to 1? Theta is very close to 1 when the sigma alpha square is all that there is, and this sigma, this eta is just nothing. There is no eta at all. In that case, what happens? So this theta is 1 or very close to 1. You cannot make it exactly 1, but it will be very close to 1, right? Okay? In that case, what are you doing here? You are doing your usual demeaning, right? So you are doing fixed effects, right? Okay? So this random effects estimator is somewhere in between the two, right? You have pooled OLS at one end, which is the right thing to do if there was no individual variation, and fixed effects on the other end, which is the right thing to do if there is individual variation is all about it, right? So the idiosyncratic part is not there at all, right? So random effects is somewhere in between. It's a convex combination of those two. Okay? It's a halfway house. Right? Together so far? Short break? But before that, any questions so far? You're comfortable with this, right? So nice and simple? Okay. Let's do a 5-7 minute break and return. All right, let's make a start. Okay, so what we have just seen is that the random effects estimator is somewhere in between the pooled OLS and the fixed effects. Okay, so keep that as a given. Now, what are these two estimators? So the fixed effects estimator uses only within variation. So fixed effects uses only within variation. First differencing also uses only within variation, but less efficiently. So let's talk about fixed effects under the strict exogeneity condition, less efficiently. So between estimator uses only between variation. So what does the random effects estimator do? It uses both within and between variation, right? Okay, that can be seen from several contexts, but also from the context that what you are doing is quasi-demeaning. You are doing demeaning to some extent, so therefore you are using within variation, but you are not going the full way, so that you can retain some of the between variation as well. So you are using both between and within variation. In fact, I've shown you this, that the random effects estimator is somewhere in between pooled OLS and the fixed effects estimator. Something else can also be shown, that this random effects estimator is actually an average of the fixed effects and between effects. Okay? And these weights are the inverses of the within and between variation. Similarly, you can also show that the pooled OLS, so this is sort of another way of saying the same thing, is a matrix weighted average of the fixed effects and between effects estimator. All right? So all of these estimators are actually pretty similar to each other. They are using different moment conditions in different ways. Okay? But when you use the pooled OLS, of course it is a combination of these two, but that combination, or it is an average of these two, but that average is not optimal. The optimal way to do this is random effects. Okay, so look at Baltaji's book, you will find that he shows this, derives this exactly, right? What does that mean? That means that suppose both sets of moment conditions were correct, all right? Then we would like to use both within and between variation, right? Because both sets of moment conditions are correct. So x is orthogonal to alpha, x is also orthogonal to eta, in which case we would like to use both sets of moment conditions, both within and between variation. So what are the estimators which use both? Fixed effects only uses within variation. Between effects only uses between variation. So we now have two estimators which use both within and between variation. One is random effects and the other one is pooled OLS. Now if we were in the business trying to use both between and within variation, then one should always use random effects. Why? Because it is more efficient. Why is it more efficient? It is more efficient because it is using the structure of the data, right? In order to split the variance into two parts, it is actually using the fact that each individual is observed over t periods of time. Another individual is also observed over t periods of time. That information is not used by pooled OLS. And because it is not used by pooled OLS, so therefore pooled OLS is less efficient. It is not using the full information available within the data structure. Okay? So pooled OLS uses the same moment conditions as random effects but less efficiently. So given the choice between pooled OLS and random effects, you might as well use random effects. Okay? However, if the between moment conditions are invalid, then what happens? Pooled OLS is wrong, random effects is also wrong, inconsistent, right? In that case, we have to fall back upon only estimators which use within variation, which are fixed effects and first differencing. Out of these two, fixed effects is more efficient because it uses the full set of moment conditions. Provided these moment conditions are held up, then fixed effects is preferable, right? Okay, does that make sense? So we are putting all the estimators that we have seen so far on the table and now trying to decide what is it that we want to use in different conditions, under different conditions. Okay, so what about covariance estimation? Well, it is simple given the covariance estimation that we have done earlier. It is a simple application of that. So with conditional homoscedasticity and no within panel autocorrelation, all right, that is an assumption of the model. So this guy is going to be consistent, and it is simply the variance covariance estimator reported after OLS on the quasi-demeaned equations, right? So you estimate your theta reasonably efficiently, right? And then do your quasi-demean your data, and after doing that ordinary least squares, you do ordinary least squares, and this is simply that variance covariance matrix estimation. So there are no degrees of freedom adjustments required here. Why? Because we are not explicitly estimating the nuisance parameters, so we are not actually losing any degrees of freedom here, right? We are using both within and between variation. What happens if you have heteroscedasticity or autocorrelation, right? Then a random effects estimator is consistent but is no longer efficient. If you suspect that either of these conditions are true, then we should be using heteroscedastic and autocorrelation consistent covariance matrix. But now we sort of start landing into no man's land, right? Because the moment you are trying to obtain these, cluster robust covariance matrices, you know that your variances get inflated, estimated variances get inflated a lot, right? So now there's a question of are we really still doing better than pooled OLS? All right, so that is an empirical question, right? So it's context specific. Okay, random effects estimator. Back to our standard example. Union membership and wage determination. Okay, so wages on the left hand side, we have education, experience, union membership on the right hand side. Okay, so we are doing random effects estimation. Remember, it is a two-step estimator, right? It is two-step rather than two-stage. Just know the difference between the two, right? Okay, so Mark has discussed this in the context of two-stage least squares. Okay, right, so it is a two-step estimator. In the first step, you obtain estimates of these error variances. Okay, but you estimate this reasonably efficiently. Once you have done this, then you do quasi-demeaning and run ordinary least squares. Okay, so that is a efficient GLS, right? So this is going to be done automatically using econometrics packages. In Stata it is, well, it is the default in Stata, right? If you do panel data regression, the regression command for ordinary least squares is regress, right? For panel data it is very similar, xtreg, xt standing for panel data commands, okay? And the default is GLS random effects. Can you do this random effects estimation efficiently? This is a two-step process, right? So the errors in the first step are going to creep into the second step. So it is not fully efficient. Okay, so what we have just discussed here, the GLS, feasible GLS estimation is not fully efficient. Is there a way to do this efficiently? What is the most efficient estimator you know about? Anyone? Come on, don't be shy. You know efficient estimation, right? We have talked quite a bit about efficient estimation. How do you do efficient estimation? Maximum likelihood? Can you do maximum likelihood here? Yes, provided you assume that these two guys are both normal. All right? Assuming that, you can do efficient estimation, right? So that is maximum likelihood. Okay? So instead of RE here, or leaving this blank in Stata, if you said ML, then Stata is also going to provide you random effects estimator, but that is under the maximum likelihood assumption. That is maximum likelihood, right? Under Gaussian error assumption. Okay? Instead of RE, if you put in FE, you'll get fixed effects. All right? If you do BE, I think you get between effects. There's a way of getting between effects. What the exact command is, I've forgotten now. You can get between effects, estimator as well. What is remaining? First differencing. Okay? There is no default command within Stata to do that. First differencing is first differencing. You first difference all variables and put that into your reg command to get first differencing estimators. I think we are going to see that in the lab as well tomorrow.
How would I do the maximum likelihood here?
ML here. How would I do a maximum likelihood? Well, you have to assume both these components are normal. So you need full distribution assumption, no, to do maximum likelihood. So once you do that, I'm not saying that that assumption is, valid or justified, right? So suppose you make that assumption, then you can estimate this efficiently. Okay? So for the coefficients on variables that vary over time and across individuals, for example, experience, union status, you are using both within and between variation. Okay? However, for variables that only vary across individuals, for example, education, you are using only between variation, right? So that is what random effects provides. So what about the endogeneity concerns? They stay, right? Because if you're doing random effects, you are actually assuming that this guy here is orthogonal to the x, right? So this endogeneity concerns still stay, right? So that is important. Okay? So for example, if education was somehow correlated with your unobserved heterogeneity, okay, or union membership was correlated with unobserved heterogeneity, then you will have trouble here, right? So you will get inconsistent estimation. Okay? So here's going back to the question of between and within variation, and I was just discussing with one of our friends here during the break, right? Okay, so what do these mean, these guys, right? So this beta 3, now union membership we have discussed that is likely to have both between and within variation. Is the effect on wages the same? Well, it is a hard question to answer without the context of an appropriate theoretical model, right? I don't have a model here, right? So I can't really answer that question. So one has to think through the question carefully. Suppose it is the same effect. What do you mean by that? The effect of somebody moving from a non-unionized job to an unionized job is the same as considering two individuals, one who is always in a unionized job and another one who is always in a non-unionized job. Okay? So one is within variation, the other one is between variation. Are these two effects on wages the same? I don't know the answer to this question. In some ways, this has to do with theory, appropriate theory. In some ways, it has to do with finding out with your appropriate, in the context of your data, right? If you find different estimates, then there has to be some explanation for it, right? So I said, good question, I left it there, okay? So because there are these concerns, in particular, one is endogeneity, and the second one is whether, there's an apples and oranges problem if you mix up between and within variation. Sometimes people prefer to use only the fixed effects estimator, because that is cleaner, right? So you know what you are getting, okay? But then, if you're doing that, then you are throwing all the between variation out. So you should be able to look at that as well. So a good example of this is actually when you do cross-country regressions, you find that the fixed effects are very important. How do you understand fixed effects here? Typically, you understand them through institutional contexts of different countries, institutions. All right? So what you might want to do is, you might want to, first of all, do fixed effects to understand within variation, or to estimate the model exploiting only within variation. Then you might ask, so where do these institutional things come from? Do they come from the rule of law? Do they come from, colonial history? Do they come from something else which has to do with these countries? All right? So they are interesting questions in their own right. How would you try to understand that? Potentially using between effects estimator, or sometimes you can also use, if there is only one source of variation for each individual thing, then you can also use random effects and stuff like that, right? But it is sort of an open question, how exactly you do it. There is, as I said, another estimator which is available, which I do not discuss, the Hausman-Teller, which does a bit better in those contexts. Okay. One other point, with regard to experience. Earlier when we were doing fixed effects, we saw that this coefficient here, beta 2, is really a time trend. Remember that? Because every year, 1 year to the next year, a person who is employed, their experience increases by 1, which is the same increment as 1 year to another year, right? So it is really like a time trend. When you are doing random effects estimation, does this persist? No, it doesn't. So that interpretation breaks down. Okay? So you have to now interpret this beta 2 simply as an impact of experience. Okay? So of course you can obtain an estimate of time trend itself directly in this case, and just add a time trend to your model. Okay, just add t as an additional variable, and that is fine. So that is going to give you an estimate of time trend. So now what we do is we add a beta 4 t here. Okay, and this beta 4 is now going to give me an estimate of the secular changes over time. Okay? Now, back to the critical question as to the moment conditions, right? So what were the moment conditions that we have used? So the fixed effects conditions, which are relatively innocuous, and what were those? Those were xit, eta I, I'll say s is equal to 0, all right? And the other one was xit, alpha I is equal to 0, right? So these were the within moment conditions or fixed effects moment conditions, all right? And let us call this the random effects moment conditions. So what does the fixed effects estimator do? It uses only this one, the first one. What does the random effects estimator do? It uses both. But if both of those conditions were valid, in particular if the second one were valid, then random effects is more efficient, right, than fixed effects. Whereas fixed effects is consistent under both sets, right? So whether the second one is valid or not. So long as the first one is valid, fixed effects is consistent. So that now suggests that we can use a GMM distance test for the additional moment conditions. Right? What is this GMM distance test? You guys know this already, so that is a Hausman test. So we can do a Hausman test of fixed versus random effects. Okay? So the conditions for the equivalence of this and the Hausman statistic H are are met here, right? So, so. Is this test good in practice? Well, there are several problems with the standard version of the test, and you will come across this quite frequently. Means in your labs, you will come across it. In past exam papers, you will see several instances of this. There are two problems basically here. One is that, of course, these two are equivalent under the standard assumptions that we make about the errors. But these standard assumptions are often not validated in the data. And therefore, there are several problems which come about. One is that you know that the Hausman test uses a approximation, first order approximation to the variance of the difference in the two estimates. So how do you do a distance, GMM distance or Hausman test? You take the beta hat FE minus the beta hat RE, right? Okay, so this is a vector. Okay, and then you take a covariance matrix of the difference between FE and RE, all right, and then you do a beta hat FE minus beta hat RE prime. Okay, depending on whether you are writing that as a column vector or a row vector, you have the prime in the appropriate place. But that is your distance test. Okay? How do you estimate this? The standard way or the traditional way, the Hausman way, was to estimate that as variance hat FE. Which one has larger variance? Yeah, this one. Minus variance RE. Up to first order approximation. In practice, what happens is that when you do this, you find that you get a covariance matrix, or you get a matrix which is not positively definite. That is often a problem, right? Then you have to do something else, right? But still, approximately, this test is still gives you some reasonable insights. Okay, so that is the standard form of the Hausman test. But these problems arise. So I said that in practice it is usually better to use a cluster robust test that allows for heteroscedasticity and autocorrelation. This typically happens because of heteroscedasticity or autocorrelation. Right. So this is the, so you see the prime is the other way around. Okay, that's all right. That is the way you have written it. Okay. So this is the difference, right? This is the variance covariance matrix of that difference, right? And this is just completing the distance and suitably scaled, so that is n, okay? So what does Hausman do? First of all, it approximates this variance by this guy. Secondly, it does a first order tailored approximation of the inverse and writes this simply as the difference between these two. Okay, so it turns out that this test is the same as the test between RE and BE and FE and BE. Okay, so all these three tests are exactly the same. What is it that you are saying, therefore? You are saying that this So what is this test a test for? So what hypothesis is it testing? It is testing this hypothesis, right? Okay, the second moment condition here. If that moment condition is valid, then fixed effects and random effects should give you the same results. Between effects and random effects should give you the same results. And between effects and fixed effects should also give you the same results. Okay, so all these three tests are actually equivalent. Okay, all of these crucially depend on, this assumption, right? So, yes. So the Hausman test for fixed versus random effects is based on the contrast between the fixed effects estimator and the random effects estimator. And the random effects estimator here uses additional moment conditions, so it is a test for those additional moment conditions. If this difference is huge, large, right, your H is large, what does that mean? That means that the fixed effects estimator and the random effects estimator are very much different from each other. What would that mean? That would mean that the second moment conditions there, the random effects moment conditions, they are not valid, right? So you would reject this for large difference. Okay, so if they were valid, these two estimators should be literally the same. So the fixed effects moment conditions are valid, the additional B moment conditions, so actually let me call it the B, this is really the between effects moment conditions, these are not random effects moment conditions. So these between effects moment conditions, they are not valid. So better interpretation is that it compares the within moment conditions and the between moment conditions, okay? This is an interesting question, right? This comes back repeatedly. So Mark would have emphasized this with you several times. So when you are doing a test for over-identifying restrictions, suppose you reject the null hypothesis. Okay? So that tells you that at least one of those moment conditions is not valid. But you do not know which. Turn this the other way around. Suppose you do not reject. It tells you that either all the moment conditions are valid or all the moment conditions are wrong. Okay? So now you have to think through what the moment conditions are and think through the context to find out which one is appropriate. A similar thing happens here. So when you are doing a distance test of these two, suppose you reject, well, let us think about what we reject, but suppose this is large, this H thing is large, right? H is equal to n times this, okay, that is large. This will be an inverse. Suppose this is large, it is potentially possible that this moment condition is valid and this one is not, right? Okay, that is something to ponder about in the context of your estimation or in your particular application. Why? Why might that be the case? Well, that might be the case if you have unobserved heterogeneity, but that unobserved heterogeneity is not fixed or stable over time, right? You are missing something in your regression model which is changing over time. Okay? So that is possible. So this test, so likewise both sets of moment conditions can be invalid, right? So that may also be an interpretation. So one has to think through this carefully. So the test can also be used to test specific subsets of moment conditions, right? For example, for a particular individual regressor, for example, okay? Okay. So we are now getting towards Mundlak. The Hausmann and Hausmann-like tests have problems, all right? So they are not very easy to apply, okay? And they have several limitations. So there's a question of how we can perhaps robustify them, okay? So one way of doing that is taking your original model, but what you are doing is you are also adding the means as additional regressors. Okay? So you do that, and now estimate this using the random effects estimator. So see, these guys here, they are something like fixed effects, right? In the sense that they are not varying over time, right? For individual units. They are capturing the between effects. All right? So sometimes these guys are called Mundlak fixed effects. This was first suggested by Mundlak. Now what happens in this model, the beta hat which is produced here will be exactly the same as the fixed effects estimator. Why? Because this thing is really like a